steady state error for different types of a system. So let us take a general expression for the open loop gain. Gs into Hs is equals to K times 1 plus T1s, 1 plus T2s, and so on, divided by s to power n 1 plus Ta as 1 plus Tb as, and so on. Now this form of transfer function is known as the time constant form. Now in this expression we already discussed that what is the definition of the type of a system. Number of poles, open loop poles at the origin is the type of the system. So in this expression, if n is equals to 0, it is a type 0 system, and if n is equals to 1, that is a type 1 system, and if n is equals to 2, it is a type 2 system, and so on. So number of open loop poles at the origin is the type of the system. So this is how we define the type. Now for type 0 system, let us first assume the type 0 system. Now for type 0 system, as already discussed, that the value of n is equals to 0, the value of Gs Hs is equals to K times 1 plus T1s, 1 plus T2s, and so on, divided by since n is 0, so this will be 1, so this will be 1 plus Tas, the remaining terms, 1 plus Tbs, and so on. Now this type 0 system, we want to calculate different error constants, which we have already defined the previous slide. So first of all, what is the value of Kp for this type 0 system? We already discussed that Kp is nothing but limit s tends to 0 Gs into Hs. So simply if I will apply limit s tends to 0 in this expression here, Gs Hs, since all these terms above will be 1 and in the denominator is also 1, so we're left with only K. So this will be only K. Now the next error constant is Kv, which is the velocity error constant. So this will be K limit s tends to 0 s times Gs Hs. So when I will multiply this Hs with s, let me write it here, s into K 1 plus T1s, 1 plus T2s, and so on, divided by 1 plus Tas, 1 plus Tbs, and so on. When I will apply s tends to 0, this will make all these terms will 0. So this Kv will come out to be 0. Similarly, Ka, which is limit s tends to 0, s square Gs Hs. So like in the previous case, this will be s square in this case. So s square and this remaining term Gs Hs, which we will put from this equation. So this s square will make it 0. So this will also equals to 0. So for type 0 system, the value of Kp is K, the value of Kv is 0, and value of Ka is 0. So for this, I can calculate the steady state error for the first case when the system, when the value of Kp is K, the steady state error in this case is, since the if you can remember, the steady state error in that case is A by 1 plus Kp. So this will be A by 1 plus K. In this case, the steady state error was A by Kv, and Kv is 0, so this will be infinite. In this case, the steady state error is A by Ka, and Ka is 0, so this will also be infinity. So let me again summarize this. For type 0 system, the number of open loop poles at the origin is 0, and this is the open loop transfer function for the type 0 system. For this type 0 system, the value of position error constant is K, the value of Kv, which is the velocity error constant, is 0, the value of Ka, which is the acceleration error constant, is 0, and the steady state error for these three different type of inputs is, for the first case, for the step input, the steady state error is A by 1 plus K. For the ramp input, the value is infinite, and for the parabolic input, the value is again infinite. Now let us discuss this steady state error for type 1 system. So the second type is type 1 system. Now for type 1 system, the value of n is equals to 1, and for this system the value of HSGS which is the open loop gain, is k 1 plus t1s 1 plus t2s and so on, divided by s into 1 plus ta s 1 plus tb s and so on. So this is the transfer function for the type 1 system. Now for this system, let us determine the value of kp first. So the kp is equals to limit s tends to 0 gs into hs. Now if you will put limit s tends to 0 into this expression here, this s, when you will put s tends to 0, this will make this infinite. So the value of this kp comes out to be infinite. Now for kv, which is limit s tends to 0 s into gs hs, so this value comes out to be, since we are multiplying this with the s, so this s into k 1 plus t1s 1 plus t2s and so on, divided by s 1 plus tas 1 plus tbs and so on. Now this time these two s will get cancelled, and we are applying this limit s tends to 0 in this expression. So this time this value comes out to be k. And similarly, if I want to calculate ka, acceleration velocity constant, limit s tends to 0 s square gs hs. Now this time this is limit s tends to 0, we will multiply with s square k 1 plus t1s 1 plus t2s and so on, divided by s into 1 plus tas 1 plus tbs and so on. Now this time this one s will get cancelled, and when you will put this limit s tends to 0 in this expression, this s will make it 0. So for this type 1 system, the value of position error constant comes out to be infinity. And if I want to calculate the steady state error for this step input, this value, if you can remember, the steady state error for the unit step input was a by 1 plus kp, and if I will put this kp to be infinity, the steady state error will comes out to be 0. Now for the kv, the steady state error for the velocity input was ess is equals to a by kv. The value of kv is k, so this, in this case, the steady state error is a by k. And for the parabolic input, the steady state error was a by ka, and this value is 0, ka is 0. So for this case, the steady state error is infinite. So let me again summarize this. For type 1 system, the open loop number of poles at the origin is 1, and if I will calculate the value of kp, it comes out to be infinity. And for this unit step input, the steady state error is 0, and the velocity constant kv comes out to be k, and in this case the steady state error is a by k, and the acceleration constant ka, error constant, comes out to be 0, and for this case the steady state error is infinity. Let me summarize this whole discussion. So in this table I am taking different type of signal. So first I am taking type 0 system, type 1 system, and type 2 system. And here in the columns I am taking different inputs: the step input, the ramp input, and parabolic input. So if you can remember, for type 0 system, if I will take step input, and this table I am making for the steady state error, ESS. So this table represents the steady state error for different types and different inputs, input signals to a control system. Now if you can remember, let me go to that slide. In this slide I have determined the steady state error here. Let me take a different line here. So steady state error for different type of inputs. Here I have already determined these values, a upon 1 plus k. These are values for type 0 system, and for this one, first one is for the unit step signal, the second one is for the ramp signal, and the third one is for the parabolic signal. Similarly, I have determined these values for the type 1 system also. So for type 1 system, if the input is unit step, the steady state error is 0, and for the ramp input the steady state error is a by k, and for the parabolic input the steady state error is infinite. So let me summarize these all parameters in this table. So for type 0 system, if the input is step input, so the value is a upon 1 plus k. For the ramp input it was infinite, and for parabolic input is also infinite, For type 1 system, if the step input is there, the steady state error was 0, and for the ramp input it was 1 by k, and for parabolic input it is infinity. Similarly, if I will determine these values for type 2 system, you will see that for the step input the steady state error comes out to be 0. For the ramp input also the steady state error will comes out to be 0, and for parabolic input it will come out to be a by k. So this is the overall summary of the steady state error for different types and different inputs to the control system. Let us consider this example. In this example, a unity feedback system is given with GS is equals to 40 s plus 2 s plus 1 s plus 4, and for this system we need to calculate the value of first of all we need to tell what is the type of the system, and then calculate all the error constants and the error for the ramp input with the magnitude equals to 4. Now, to solve these type of problems, first we need to convert the feedback system, the open loop gain, into a standard form. If you can remember, these we have taken GS HS in the time constant form, which is k into 1 plus T1 as 1 plus T2 as and so on, divided by s to power n 1 plus Ta as 1 plus Tb as and so on. So first we will convert this. HS is equals to 1 for this system, since it is given that it is a unity feedback system. So for this system, this value of GS HS is equals to 40. I am taking 2 common from the numerator, so this will be 1 plus s by 2 divided by s into I am writing it as 1 plus s, and in this I am taking 4 common, so this will be 1 plus s by 4, so I am taking 4 common from the denominator. So this will be this will get cancelled, so this will be 20 1 plus s by 2 divided by s 1 plus s and 1 plus s by 4. So this is the now this we can compare these two equations. So the value of k is here is 20 and the value of n is 1. So since the value of n is 1, so we can say that this is a type 1 system. Now for type 1 system, if you want to calculate all the error constants, let me go back to that slide in which we determined all the constants here. So for type 1 system, so for type 1 system, we have determined the value of Kp, which was infinite, value of Kv is k, and value of Ka is 0. So let's go back to the question. So here value of Kp is infinity, value of Kv will be k, which is 20 in this case, so this will be 20, and value of Ka will be 0. Now in the third part, we want to calculate the error, steady state error for the ramp input with magnitude 4. So for the ramp input, let me go back to this slide. For the ramp input for type 1 system, the steady state error is a by k. So let us calculate this. So for the ramp input, let me write here, for a ramp input, the value of steady state error is a by k. So this will be a is given as 4, magnitude is given as 4, and the value of k is 20. So this will be 4 by 20. So this is 1 by 5, we can say 0.2. So this is how we will solve the numerical problems based on the steady state error. Thank you.